Right. All right, we're gonna tackle the problem that we were discussing and go over it in a little bit more detail. And I thought making this video would help to create a little bit more clarity in the computation and also provide the opportunity to, review the process multiple times, especially for the problem we're going to assign at the end of this. Okay, so I don't remember exactly how we had it labeled per se, but I'm gonna go ahead and call each of the points. So we have a line with a negative slope where the y-intercept is at the point B at 0, 2, and its x-intercept is at the point A, which is 4 and 0. And so what we're trying to do is find the area bounded by the y-axis and the x-axis and this linear equation here. Okay, so I'm going to first write what we're trying to do. So find area bounded by, and then I'm going to give some coordinates here, but really it's just this first quadrant, this triangular area bounded by. Okay, so for the x values, it's going to be between the x equals 0, which is this vertical line here, aka the y-axis, and this x-intercept here, where the line crosses the x-axis, and x equals 4. But you could think of that as a vertical line running through x equals 4, since that is the, I won't draw it in, but that is another way of thinking about it. And so x is bounded between those two. And the curve, which for us is a straight line, y of x. Okay. This is y of x, and we'll need to define what y of x is. We'll have to calculate that, finding the equation of the line y of x. Okay, so that's what we're going to do. But first, note we have a right triangle. I'm going to draw what looks like the delta symbol is a triangle, right triangle. So we know, I should use the word know, the area is 1/2 base times height. And you'll notice here that the height is the length of this dimension here. Here's my right angle. And so 4 minus 0 is this length. And this height, we do the same calculation as looking at the y components, it's 2 minus 0. So this is the height of the triangle, and this is the base of the triangle. And I'm going to put a little triangle symbol underneath of it to indicate that it's the base of the triangle. Probably be better if I made it look like a right triangle. But that's actually what we're talking about. And later in a minute, that's going to look like the delta symbol, which is going to be confusing. So the base here you see is 4, and the height here we see is 2. So the area we can get from 1/2 base times height, which we get out to be 4. Okay. So whenever we can use familiar geometric figures, this new process that we're going to explore should give us a similar results. Okay. All right. So let's see what this new process if we get the same area. Okay. So I'm going to construct here a arbitrary rectangle, and notice we'll be creating many rectangles. I'm just going to draw a couple of them, and we're going to use the right endpoint. Approximation. Okay. So using the right endpoint approximation, that means that each of the rectangles that I make, and I'll try to draw a little bit bigger so you can kind of see where they're coming from. Okay, so each of these rectangles that I'm making, notice that the height of the rectangle is defined by the height of the right side. In other words, the right upper right-hand corner of the triangle of the rectangle is what defines the height. That's why this is called uh, the right endpoint approximation. Okay, so the left endpoint is very similar, just that the left endpoint would then be would define that. Okay, and so I'm going to make it. I'm going to make lots of these rectangles, and the goal, of course, is that that one kind of got squished in there, but each of these widths, we're going to try to make exactly the same, just like we were talking about on Tuesday, the first week of class. Okay. And so we're going to have lots and lots of these rectangles, and they're all going to have this height. Okay, so if you imagine this is you walking along each of these, okay, each of these rectangles. Okay, what you're counting is how many steps it takes to get to this. So this first one, it takes one step. Okay, so your x, well, if you start here at 0, right, your x 0, that's how many steps you have. That's 0. Okay. And then your next step would be at this first point, which is x1. So this would actually be the first location of your rectangle, and that happens to be the height. So that's what's defining the height. So this x1 is going to be the first uh, height of the first rectangle. Okay, and then if we step again, okay, then we're right here at x2, and so that's going to be then the second height of our rectangle. If we step again, we'll be at x3, x4, and as we can continue, some arbitrary rectangle. Okay, so I'm going to draw that arbitrary. And when I mean arbitrary, I mean I'm just choosing some rectangle somewhere in here, just to be a representative of it. Okay, I'll draw that a little bit, and I'm blowing it up a little bit just so you can kind of see where the parts are coming from. So the line is coming through like this. So imagine I'm kind of like zooming in on this part right here. Okay, so here's the line, and here's my right triangle, or my rectangle, not rectangle, my rectangle. And the angle or the line is coming through the right angle here. Okay, so its base, the base of this rectangle, um, how wide it is, okay, is going to be, since they're equally spaced between this point here 4 and this point 0 here, the delta x, which is the base of this thing. This is not the triangle AC here. What we call delta x is equal to xi minus xi minus 1. Okay, so it's this arbitrary point, xi. This is what's defining the height of the rectangle. And then this is the point before it, xi minus 1. Okay, in other words, it's just one step back. So the minus 1 is this. This was like 5. This would be 4. I think. Okay. So this is what defines what that width is. And to make sure that they're all equally spaced, so the equality here and the equally spaced, making sure each of these bases is identical, is you're going to take the length of the entire interval you're looking over and then divide it by how many pieces or how many equal sized triangles do you want. Okay, so to determine the length, we're going to take the value of the x component here. So we're going to take, we would call that b minus a over n in a general sense for the notation, but for us, b is 4 minus a, which for us is 0, and then dividing that by n. That gives us then that the number of equally spaced bases here is 4 divided by how many rectangles do we want to make. Okay. All right. I'm trying to keep everything in picture here. All right. Okay. So that's the width of this thing is 4 over n. And then if you come back up here and say, okay, so that's each of these bases. So since they're all the same, then I can count using this idea that we're talking about here. So that's one base, that's two bases, that's three bases, that's four bases, that's five bases, and keep going all the way across. And so by the time you get to the end, you'll have n bases. But since I'm somewhere in between here at any given point, all I have to do is count the number of steps. Okay. So to figure out where I'm at along this base, you would get an ith component. Okay. All right. And then to figure out the height of this Okay, so we know we're at this xi point, right? So let's look. Well, how would I define where I'm at on this? And that's what I'm trying to say with since we know our steps are all the same, right? Since we know our steps are all the same. Well, where did we start? We started at this point here, what we called C. But in general, that point will have a value of the x component will have a value of A. So we're going to call that A. And then we're going to add to that. So when A is 0, right, we haven't stepped anywhere. We're going to move one step to the right. Okay, so how do we count that? Well, we're going to call that I. And then since each of our steps are equally spaced, we'll call that delta x. And we already figured out what delta x was. So A for us is 0 plus I times delta x, which is 4 over n. So again, that's just the length of each of the steps that we're taking along this interval, going from 0 to 4. Okay. So then our xi for the right endpoint, because our steps are defining the height of the rectangle, is this value. Okay. So now we have the height of where the height of the rectangle occurs. We know how wide each of the rectangles that we're making are. And so now we just need to figure out, okay, what is the equation of this line then that gives us the height of the rectangle? Okay, and so since that is a line, we know that the y of x is equal to the slope times x plus the y-intercept. This here is the y-intercept, not the not the b that you saw up here. This is the interval, so misuse of bad notation, I apologize. But this is y equals mx plus b. We know the y-intercept for us is 2, so our problem in that regard is really nice that we know that the this is 2. And we just have to determine what the slope is. But if you notice, since we were looking at the intercepts, the y-intercept and the x-intercept, the slope will be pretty easy to calculate, uh, primarily because one of the coordinates is 0 in that case. So look here, taking the upper endpoint, okay, so the y here is 2. We have 2 minus 0, which is the y coordinate for this point. We're going to divide from that. The x coordinate here is 0 minus the x coordinate for this point, which is 4 times x. So that's the slope times x plus, and again, the y-intercept for our graph is 2. Okay. So that leaves 2 minus 0 over 0 minus 4, which is equal to, of course, negative 2 over 4x plus 2. And I can simplify this a little bit because each of them are divisible by 2, a 2 and a 4. That becomes negative 1 half x plus 2. Okay, so that's our height. That's what determines our height. And so now that we know this x is going to be replaced by this xi to determine then the height of an arbitrary. Okay. So now that we have the height of the rectangle, and so now we know the height of the rectangle, which is defined by this value right here. Okay, so this is xi, that's what we're going to plug in, and we just found out what y of x is. Okay, so we're going to take this y, or this xi, and we're going to plug it into that x to determine the height of this arbitrary rectangle. And then we're going to multiply it by the base, which is this base here, this delta x. But we found that the delta x is, for us, what we constructed equally based, size 1, 4 over n. So to do that, okay, so the area of the, what I call it, I, put that in parentheses, rectangle, is uh, base times height. Just the area of a rectangle, space times height. And so we saw that the AI is equal to the base, which was delta x times y of xi. This is the base, and this is the height. Okay. For us, that's going to equal the base is 4 over n, and the height is, let's see, negative 1 half xi. Xi was what? Oh, that was right here. That was 4 n over I. So 4I, sorry, I think I said that backwards, 4I over n plus 2. Okay, so this is the height. And this is the base. So just keeping everything together. You can see this is a problem that doesn't have a lot of inputs, and so even this seemingly simple problem has quite a bit of information, and there's lots of things that can go wrong. Okay, so when we're doing these, you got to be very careful about your bookkeeping. Okay, so again, replacing the x here with the xi, and the -1/2 and +2 is the equation of the line that defines the height of the rectangle. Okay, now that we have each of those in, okay, so this is the base of the rectangle, this is the height of the rectangle, and that product is going to give us the area. We can simplify this a little bit by noting that -1/2 times 4 is a -2, and um, we could distribute the 4 over n through, but you'll see why I don't do that in a second. So 4 over n. So I will simplify -1/2 times 4. It's going to give me a -2i over n plus 2. And I could factor out that 2 for everything, but I won't for just this minute, just to relate it back to what we were doing in class. And so now you'll notice if we come back up here to the rectangles, okay, each of these rectangles is an area. And so if I wanted to know what the total area under this triangle or under this curve is, right, this triangular area, I need to add each of these rectangles all the way down. So there's a bunch of rectangles here that I need to add. So to do that, I'm going to add up those rectangles. So the total area, which is really what we're after in this problem, okay, is equal to the sum. So this is right as a sum from I equals 1 to n. So where we're starting, where we're stopping, of each of the individual areas. The AI being each one of these has a different I, 1, 2, 3, 4, 5, so on and so forth. Okay. But if I plug that in, equals 1 to n. If I plug that in, I'm going to plug that in here. Okay, so remember the area is the base, and I'll put a little I script down here just to indicate that it depends on where you're at or what pace. For us, since all of them are the same, we can actually factor it out of the constant. But in general, it will be the case that those will be times the height. Okay, since our areas are rectangles, so that's what we're plugging in, and that's kind of what we have up here: base, height. All right, let's go ahead and do that. And then we're going to use, after we plug in the values here, 4n over -2i n plus 2, we'll use closed form properties that we've discussed to simplify the sum, and then we'll take the limit as n goes to infinity to create the total area. All right. Notice that this sum does not depend on n, so this n term actually is a constant. So I can actually pull out that n term, and likewise, we saw that the constant does not affect the sum; it just becomes a product of the sum. Okay, so I can use the linearity of the sum to go across each of these terms. So in the next couple of lines, I'm not going to compute the sum yet. What I'm just going to do is get the sum ready to be computed. Okay. So the first step, I'm going to pull out this 4n from everything that's being multiplied there, and this sum does not depend on it at all, which is why I didn't distribute it in up here. Okay, and so I'm just going to leave that way out in front, and then I'll deal with that at the end of once we have the sums computed. Okay, so that's 4n is out of the picture since being multiplied by everything. So I just have this -2i over n. So I does depend on the sum, but this -2 over n does not. So I can factor that out of the sum. 2 over n, sum I equals 1 to n. Just the I. So the only thing that's left over there Okay, so I have this out in front of everything. This negative 2 over n is here, and then I just have an I there. Okay, and then I have another term here, a sum. So I'm going to use a linearity and use this sum, and that's going to go into, but that 2 is a constant with respect to the sum. So I have plus, and moving that 2 out, what am I adding up? Well, I equals 1 to n. I just have a 1 that I'm adding up there. Okay, all right. So now we have this set up so we could use the closed forms, the sum of I with a linear power, and then I'm just going to have n of these values here. Okay, so let me get a fresh sheet, and I will keep that in the picture so I can kind of see where this is leading to. All right, so we see here we have uh, 4 over n times negative 2 over n, the sum I equals 1 to n of I plus 2, the sum I equals 1 to n of 1. Okay? And this was the total area. So uh, we know that the sum, just kind of pulling this out, so this part right here, the sum of I equals 1 to n of I is equal to, well, that's like 1 plus 2 plus 3 plus 4 plus plus n. Okay, so to compute the closed form of this, or if you're wondering where that formula comes from, think about this. What if we did what we call Gaussian pairing, and we saw, okay, we have n times, or n plus 1, that would give us a sum of n plus 1. Okay, and what if we did the second term here plus the second term here? Well, the second term would be 1 less than n, so this would be 2 plus n minus 1, because it would be one term less than n. And if we added these together, this is equal to n plus 1. And so if we keep doing these pairings, what you're going to find is that you have n plus 1 as a common factor in each of those sums. And if we counted out, well, how many of those n plus 1 factors do we have? We have n of them. And so uh, we recognize that we have n plus 1 factors, but we're double counting them. So we want to divide that whole amount by 2 to remove the double counts of the factors that we're getting. Okay, so the closed form for this is n times n plus 1 divided by 2. And so that's what we can replace this one by. And this one, if we look at the sum here, well, what is it saying? It's saying that you have the sum I equals 1 to n of 1. Well, that's the saying you have 1 plus 1 plus 1 plus 1 away. Well, if you add up all of these, right, how many ones do you have? You have n ones. This is 1 plus 1 plus 1 plus 1 plus 1. We have n ones, okay? And so the result is this sum is just going to be how many ever n's you have computed. Okay. So utilizing this and this, using these two, we can rewrite this total area part. Okay. So I'm going to write the arrow like this, and you can read that this arrow means this implies, which is mathematical notation. This implies, okay, that 4 over n minus 2 over n. Now this sum of I, is going to be replaced in closed form with this n plus 1 times n divided by 2. And then we have plus 2, and then this sum gets replaced by, well, there's n of them, right? So that sum gets replaced by n. Okay. And now we're going to find a bunch of things you're going to simplify. Okay, so you'll notice that the 2 and the negative 2 here cancel. And look, I have an n factor and an n factor. So those are going to simplify out. And so I just have a negative that's going to be distributed to the plus 1 and the n here. Okay, and I'm going to keep the 4 over n out in front. So this becomes negative n minus 1 plus 2n. So it simplifies quite a bit. And then I have 2n minus n. So that means that this is going to simplify very nicely to n. It looks like minus 1. Okay, and now we can distribute the 4 over n. Finally, we can distribute that through each of those terms. And we get that you have 4 over n times n is those four, the n's are going to cancel. I'll write that out just so we can see what's happening there. And we get minus 4 over n. So the result is 4 minus 4 over n. Okay. And now, if we consider going back to the original problem, if we imagine that we're going to make infinitely many of these rectangles, okay, then each of these will just become the rectangle will become just a single dot, essentially just a line along those. And so in that limit, then, okay, so if we take the limit as n goes to infinity of the total area, okay, that means that the limit as n goes to infinity, this is of the ith areas. Okay. Making sure you can still see it. Try a little bit more room. There we go. Okay. Then the limit as n goes to infinity of 4 minus 4 over n. Okay. Using the linearity of the limit, right? The difference of limits is the limit of the difference. The constant term here doesn't get affected by the limit here. So this is just going to be 4. And 4 over n, as n goes to infinity, this term is going to eventually go to 0, just leaving the constant term of 4. So the total area turns out to be 4, which we saw earlier was the same result from the triangular formula. In fact, if we were to be specific with these being more generic values, we would have arrived at the formula for the area of a triangle. So there it is. That's how we're utilizing the Riemann sum to calculate the area of the triangle. Okay. Now, going to the problem I'm going to challenge you with, it's going to be very similar. The major difference will be that the height of the rectangles will be a little bit more uniform. So if I draw a shape like this, that wasn't a very good twist there, but here's the function for y. Okay, so y is equal to, let's call it 4. And, no, I think the height was 2. Yeah, sorry. Let's call it y equals 2. And we're going to go, so this is trying to keep the same or similar setup. So this was, call it b is 0, 2. This point here was a, which was 4, 0. This point here was c, which was 0, 0. Okay. And this point here was is the new one. We'll call it d, and that's going to be the x coordinate of the a and the y coordinate of the b. So it'll be 4, 2. Okay. And so the graph here is for y equals 2. So the area I'm going to ask you to find is this shaded region. So what is the area? The graph uh, y equals 2, bounded by x equals 0. that's the vertical line here at x equals 0, known as the y-axis, and x equals 4. So you already know that it, and also above the x-axis. I don't think I said that at the beginning of the video, but that's what I meant, above the x-axis. So it's that region that I showed there. Okay, so find it two different ways. Meaning, find the area using a geometric relationship, and then find the area using the sums approach with the rectangles, right? I hope that was helpful, and I'll see you in the next video.